Good morning, everybody. Welcome back to the third day of our AI and networking workshop. We are very delighted to be back. We have three wonderful speakers today, and we're going to open the floor with our first speaker, Pavan Balaji. He is a research scientist at Facebook AI. Pavan's research interest is very vast, including HPC hardware software co-design for AI workloads, which is going to relate it to his talk. And he's also done a lot of parallel programming work. Pavan has several publications and many awards. He's also a well-known speaker in academic venues. So we're very excited to have you, Pavan. With that, take it away.
Thank you, Manya. Thank you for inviting me for this talk. And it's my pleasure to be here. I'll try to keep the talk short at a high level. I've recently joined industry, so whenever I used to listen to industry talks, I was somewhat annoyed about the lack of detail. So I'm on the side of the industry fence now, and I apologize. There are some things I cannot talk about, but I will try to give as close to the actual details of our workloads as I can get away with. So apologies in advance, but hopefully it's still useful to some degree. So this talk is about some of our key workloads that we use, AI workloads that we use at Facebook, and it's very network centric. So I'll start off with some overview of the workloads, then I'll dig deeper into how we use our networks, what our constraints are, and things of that sort. All right, let's see if we can get this moving. Okay, so I want to start off by giving a little bit of a picture of the importance of AI at Facebook. So AI is basically used everywhere, or almost everywhere within Facebook. Okay, it's used for all of our applications, all of our services, all of our business needs. Everything is mostly driven by AI within Facebook. There are a few examples that I gave. This is not the only set. This is just a few examples of where we use. We use it for our video content. We use it for our, when you go to our Facebook wall, the feed content, the ranking, our ads, our search, they're all AI driven in the backend. We also use AI for other topics like computer vision, speech, hate speech recognition, for example, translation and things of that sort. It's basically used in all aspects of our system. And it's used, we have models running on very high-end HPC systems in the backend, and they get moved to our other platforms, mobile platforms or glasses and so on, and they're used with inference in all of these systems. So it's kind of embedded. It's like sort of like a central piece. It's like a core piece within Facebook, and it's kind of spread out everywhere in all of our business needs. We use a lot of models at Facebook, different classes of models, if you will, but not all of these models are the same. They have very different system characteristics, if you will, or performance characteristics, what kind of architectural needs they have, and so on. They're very different characteristics. I kind of want to separate out these models into two broad classes. On one hand, we have these content understanding models like computer vision, like natural language processing, hate speech recognition. All of those are very compute heavy. So that's the left part of the left chart, if you will. Those are very compute heavy. They're much more, lot more parameters are used. So model sizes are large. Then we have these things called recommendation models. These are the ones that we use in our ads and feeds, for example. Now, these are not as compute heavy. You can see on the chart, they are further down on the left chart, these models, but they are much larger with respect, or almost at the top of the scale with respect to the size of these models. So on the right-hand chart, you will see that they are very large models that we're using, but they're not as compute heavy in some sense. So they kind of stress the other resources of the system. Here's a quick look, as like a very brief look of how these models look like. They have these set of dense features and sparse features. And the dense features and sparse features are kind of used together for these models. This is kind of the part that makes it really complex from from an architectural standpoint. They kind of stress various aspects of the architecture. In fact, there is a kind of a description that we use within Facebook. If you pick any part of the computer system architecture, right? Pick a processor, pick cache, pick memory, pick network, whatever part you like, or say whatever your favorite piece of the computer architecture is. And these models, some of these models, mostly the recommendation models, they would stress that part of the architecture. They're so wide-ranging in respect to the architectural requirements that they have. They kind of stress all parts of the system architecture. More recently, even on storage systems like SSD and so on as well. Again, this is a quick overview slide. Just please bear with me till I'll go through this overview before I jump into the network aspects. So this is a picture I showed in the last slide. Here's a high-level view of what's going on over here. We have dense compute pieces. We have the top NN and bottom NN. These are dense compute. These are very compute heavy, so they kind of stress the processing system a lot. They are data parallel. They already use communication between the processes over the network. Then we have the sparse features. These are huge. They're tens of petabytes, large terabytes scale at this point. And they are very heavily bound by memory capacity and memory bandwidth because the lookups are very sparse. So they're very bound by the memory both capacity and bandwidth. And they send, when we exchange this data, they send this data all over the network. And basically, it's a peer-to-peer communication all through the network. So that makes it very all-to-all communication network bound as well. So we are bound by compute power, processing systems, and cache, if you will, on the compute-heavy parts, dense computes. Then we are bound by memory capacity, memory bandwidth, and communication network bandwidth for the sparse features or sparse parameters. So that's just a very high-level picture of the architectural needs of this. Now, this workshop is about networking. So what's the deal with the recommendation models and the networks? This is not to say that network is the only bottleneck for these systems. We have these recommendation models have bottlenecks on, like I said, memory system, processing system, and so on as well. But in this particular talk, I'll just focus on the network part of it because that's a more relevant part for this workshop. So let's talk about how this relates to the network subsystem. So I think I might have made this point earlier. Recommendation models, unlike many models, so we have many models at Facebook, but recommendation models are special in that they are some of the most demanding customers for the network subsystem. Okay, there are two key operations that happen over the network. And there are many operations that happen, but there are two operations in particular are very network intensive. I'll talk a little bit about these operations. The first is the dense parameter synchronization. That happens using an all-reduce operation. I'll talk about that a little bit. The second is the sparse feature pooled embedding exchange that happens. That happens through an all-to-all operation. Now, Facebook's current workloads, as well as the future models that we expect to come out in the next 5 years or so, they're all very communication heavy, very extremely network heavy. For the dense parameters, we're talking about billions of dense parameters. You can kind of derive it from the chart that I showed a few slides ago. This is about gigabytes of data to exchange per process. Okay, so if you have like 1,000 processes, each process is contributing several gigabytes of data. My apologies, I can't give the actual number of how many gigabytes, but I think you can look at the chart. If you look at the chart closely, you might be able to derive that on your own. And we have trillions of sparse parameters. We already reached the trillion parameter mark this year, and it's growing rapidly. So we have trillions of sparse features, and we have gigabytes of data to be exchanged per process for that as well. And if you can imagine, right, this entire training, training is an iterative process. So each iterative loop we are exchanging all of this data. So if you can imagine that, each training loop takes, I don't know, like a 10 millisecond granularity or something. Within that 10 milliseconds, we have to do all of our compute. We have to do all of these gigabytes of data of exchange for the dense parameters. We have to do another gigabytes of data of exchange for the sparse features or the pool embedding exchange for the sparse features and so on. And all of this has to happen within that window. So it kind of puts a lot of pressure on the network. Now, this is the networking workshops. I hope this is this slide is redundant. I hope everyone knows how collective communication works. But just in case, let me kind of give a high-level collective communication 101 over here. So it's essentially it's a group of processes that are exchanging data. So we have hundreds or thousands of processes that are sitting, exchanging data. They all they're computing on these training models in parallel, and they are trying to exchange data between themselves. So like I said, there are two types of computations that happen. One is the all-reduce communication operation, where each process contributes some data, in this case, A, B, C, and D. And at the end of the all-reduce operation, every process has some function of all of this data. In this particular case, the function here is summation. So every process has a summation of that data. And in this, as the example I gave, each of this A, B, C, D is gigabytes of data. So every process has summations of these gigabytes of data. On the right-hand side, we have all-to-all, where each process has a bunch of data. Again, gigabytes of data. A0 to A3 is about a few gigabytes of data. And you do an all-to-all, it does like a matrix transpose, if you will. So this left side matrix is kind of transposed on the right side. So every process gets a part of the data from the other processes. So as you can imagine, it's like a fully connected peer-to-peer communications. Every process is sending a chunk of data to every other process. So that's just very high-level collective communication. I hope everyone already knows collective communication, so this is redundant. But I just put that slide together to kind of give you an idea of what kind of bottlenecks we're running into. So we have these two things, like I said, all-reduce and all-to-all. In the all-reduce, it's a somewhat of I don't want to say it's an easier problem, but it kind of stresses the different parts of the network. So traditionally, we do like a tree sort of all-reduce operation, which means we move our data to our neighbors. All of the communication is neighbor process communication at the bottom of the tree. That's where the most of the data exchange happens. As the top of the tree, the amount of data exchanged is lesser. We do more further out communication, not neighbor communication, but the amount of data is lesser. So this is the kind of a pattern that we see via all-reduce. What that means from our network perspective is that we have a very high requirement on the injection bandwidth. So if you have a machine and you have like a network adapter attached to it, the amount of bandwidth that we require from the network adapter is very high for all-reduce operations. Also leafs, which are at the bottom of the tree, we have very high bandwidth requirements. At the top of the tree, right, at the spine switches, for example, we don't have as much bandwidth requirement. In fact, if you design your algorithm for all-reduce in the most efficient way, theoretically, you only need exactly the same amount of bandwidth as at each node as the spine switch. So you need the bisection bandwidth has to be at the same as the injection bandwidth for all-reduce. So we don't have a very high need for a very high bisection bandwidth for the all-reduce part of our communication. This is a dense parameter exchange. Now, the sparse parameter exchange, the sparse feature exchange, on the other hand, is very all-to-all bound. So now all-to-all, like I said, it's a peer-to-peer communication. So it's very bisection bandwidth bound, because every process is sending data to every other process, and all processes are doing the same thing. So we're kind of dumping a lot of data. Remember that each process is dumping gigabytes of data, and we have hundreds or thousands of processes that are all dumping gigabytes of data onto the network. So we kind of stress the bisection bandwidth part of the network significantly. So they have very high requirement on, for example, of spine switches, if you have like a factory class sort of topology. The requirement of the network injection bandwidth is slightly smaller, but not too small. So what these two together essentially point to is that because of this nature of our recommendation models, where we have some parts that are all-reduce bound, some parts that are all-to-all bound, we end up in the situation that we have very high injection bandwidth requirements and very high bisection bandwidth requirements that we are trying to kind of put systems together which can support both of these capabilities. So just as a quick reality check with respect to where we are today on network systems. Right? So if you go to the website of most network vendors like Mellanox or whatever your favorite network vendor is, we see that we have network adapters of about 200 to 400 gigabits per second today. And the next generations could go up to about 100 gigabits per second, 800 gigabits per second, 100 gigabytes per second. Network switches today can support similar speeds, but are bound at the crossbar level. They're bound about 30 to 64 port crossbars. That's a full ASIC crossbar at 30 to 64 ports. We can build a factory switch with a higher number of ports, but that's no longer a crossbar at that point. Our recommendation models today that we use, and more so in the future, unfortunately, the network requirements are much higher than what the state-of-art networks provide. Okay, in fact, we are so network bound for both the injection and bisection bandwidth that we cannot go with a single network adapter. We have to build out systems with multiple network adapters to be able to utilize, to be able to kind of dump the data fast enough for our models to train quickly enough. In fact, we are not there yet, but we are quickly getting to a point where we are not just bound by the network bandwidth, but we are bound by the actual I/O capacity of the socket or of the GPU, if you will. This is a picture from a NVIDIA A100 system. That's the current system that's available in the market. You'll see that each socket you have a PCIe lane that's coming out going to the CPU, and you have a bunch of NVLink lanes that are going out. Each NVLink is about 25 gigabytes per second, so that's 200 gigabits. You have 12 of them. So ballpark 2.5, 2.6 terabits per second of bandwidth we have, I/O capacity we have for the GPU. And that's unfortunately a little too small for us for our training workload. So we're kind of getting to a point where we are bound by the I/O capacity itself. It's not the network. Even if we buy 100 network adapters per server, we are getting a point where the socket or GPU itself cannot push the data out fast enough to even use the network adapters at that scale. So we kind of have to think about other ways of trying to optimize this. I am almost out of time. Let me just give you like a 30-second overview of the communication libraries. We rely on a lot of collective communication, like I mentioned, already use auto, gather, reduce, and so on. There are many collective communication libraries available in the HPC world, such as MPI. But we don't use MPI within Facebook, at least not in our internal systems. We support it externally, but not in our internal systems. Why is that? The reason is that MPI is a very generic communication library. It kind of mixes a lot of things, tries to support many things. Because of this generality that MPI provides, there are a few things that it cannot do efficiently. I will not go into the details of this. There's a paper, you can read through this. But essentially, to do zero copy RDMA sort of communication, it has to do a lot of control message exchange. I don't have time to go through this. Maybe we can discuss that over a beer or something. But it has some limitations that we kind of cannot work around in MPI. So we use other alternate collective communication libraries that take advantage of Facebook characteristics, like we have no multiple groups of processes. We don't have dynamic communication patterns. So very static sort of communication patterns. We don't mix all-to-all and point-to-point operations. So this static sort of communication patterns helps us get better efficiency out of the network. That doesn't kind of reduce the theoretical network speed that we need, but at least tries to get high efficiency out of whatever networks that we have. Okay, I think I'm out of time. So just to conclude, AI is a big piece within Facebook. It's used everywhere within Facebook. Not everywhere, but most places within Facebook. All of our business needs, everything are met through AI. And essentially, enabling and optimizing AI workloads is, for all practical purposes, an existential requirement for Facebook. Okay, it's kind of our entire business model runs around that. And recommendation models are very unique. They are very stressful for various system resources. I talked a little bit about the network, but they are equally stressful for other systems like processing and memory subsystem and so on. That's all I have. While I take questions, I'm going to, some smart person told me that never waste an opportunity to have screen presence. So I'm going to leave this open. We are looking for people to join us, either as a full-time opportunities, internships, or as a sabbatical in research positions. I leave this open over here while I take questions. Thank you very much.
Thanks a lot, Pavan. Thank you so much. Very, very insightful. There is one sort of a clarifying small question about earlier in the talk, you had a notion of S-days. If you can clarify what you had in mind there.
Yeah, it's a petaflop per second and times days. It's the speed that we need per day in some sense. It's a metric that we use within Facebook. But I would recommend not to get too hung up on that particular number, because as you can imagine, that's only for our benchmarks. It's not our internal workloads. That's only for external pieces. It's more to show that the recommendation models have a much lower compute requirement than the content understanding models, if you will. That's the intent of the chart, not the actual numbers over there.
While folks are typing their questions, I want to get your thoughts on, yesterday we had a talk from Microsoft saying the benefits of having reconfigurable optical networks to change the topology based on the traffic pattern of large-scale training workloads. And through other collaborations, say colleagues like Divatsa, we've been working with Facebook on understanding these recommendation models. I want to just collect your thoughts and see if we can benefit from your insights on what do you think? Do you think these approaches would help if you have an optical network in the middle to change based on traffic demand?
Right, absolutely. I think they do. The core network infrastructure, the core model infrastructure itself doesn't change, obviously. But most of the network requirement is based on our workloads, like our samples and data samples that we did. And we noticed a huge discrepancy in the, let's say, the distribution, sample distributions, even when we do training based on North American workloads versus Asian workloads, or in the daytime workloads versus nighttime workloads, because there is a big kind of a user difference in what kind of things are interesting to users at that time. And this, today our models are very static. Right? We use our static models. So we have this static distribution of data that happens and static communication pattern that happens. And this results in a load imbalance between processes, because they are tuned for an average case of load that happens across different processes. And morning users might stress table A and B, evening users might stress table C and D. But if the distribution of these tables was static, you have this load imbalance of which processes are doing more work. So we need some form of quote unquote redistribution of traffic. Now, whether that's through the network itself being redistributed or tables being redistributed, they're just two different solutions for the same problem. But yeah, some reconfigurability of the system in some sense.
I see. I love how you focused on DLRM as this challenging sort of a DNN training workload. And it seems like our audience is also interested, and they're sort of asking, is there any samples, maybe Python code available for this kind of research in GitHub?
Yeah, so the so DLRM is the open source, the benchmark, if you will, that kind of emulates our ads and feeds workloads that we use internally. It's not, you obviously don't get the data, but you can use simulated data to try to get a little bit of a feel of how these models work, how these embedding tables work, and so on.
Right. Actually, Facebook has indeed released the DLRM like GitHub code, and we can just dig it up and put it in chat. And we don't really need actual data. We can just use synthetic data for network requirements. Okay, there's another question from Anthony. How much time does your team spend applying a data scientific-centric view to ML problems versus model-centric?
Everything we do is data-centric. It has to be data-centric in some sense, right? Because it is what our data dictates. And we kind of, I don't know if there are two different things, because we co-design our models based on where our data is leading us to. So I don't view those as like two different things. Our models, in some sense, are auto-generated based on the data samples, or some summarization of the data samples. So model parameters, if you will, are auto-generated based on that. So it's we don't quite distinguish them that way internally.
It's interesting, just as a comment, that actually relates back to the question to Vince Poor on the first day, if you remember.
Right. Yeah.
Which was around doing the merging of distributed models in Flock. So actually, I just wanted to ask a follow-on question to Pavan based on that. So we've heard in the workshop about basically federated learning, where you learn more models locally and then you combine them, versus models where you pre-process the data, versus systems where you pre-process the data but then develop the model centrally. What's your view on those differences? It's kind of a follow-up. It's a meta question based on the last one. Yeah.
I am not sure I am really the right person to answer that question. I can tell you that at Facebook, for our core models, we do not use federated learning. We do a very tightly coupled training of the models. So they run on a supercomputer. They are very tightly coupled, very high-speed network between them, all the HPC bells and whistles, if you will. Now, I am not enough of an expert to say that federated learning is useful or not useful. Maybe it is. I'm sorry, I don't know if I can give a good answer to that.
The scale of the model sizes between federated learning and, like, say, DLRMs, like, very different. Besides DLRM, do you think there's another, maybe, like, as academics, yes, we should pay attention to DLRM and on the mobile setting to federated learning models, but what else do you think is an important sort of model structure that we should think about?
So DLRM is just one type of model, right? We have a lot of these computer vision models or other models like the NLP, natural language processing models, that we pay a lot of attention to. The reason I didn't bring those up today are they are somewhat not, from a network perspective, they're not as interesting. That's the reason why I didn't talk about them today. But at Facebook, of course, we use a lot of those internally as well. They are very, they don't have some dense parameters, some dense features, some sparse features sort of distinction. They have essentially just dense features and dense parameters to compute on those. So we kind of have a very all-reduce-centric view of that. And since all-reduce doesn't, and very small, much smaller parameter sizes, so since we don't have that much network pressure from those, I didn't bring that up. But from a computation perspective, of course, they're very interesting for Facebook needs.
Yeah, that's a really great point. Thank you so much, Pavan. We're very insightful. Really happy to have you here.